So in this question, basically Joey has A distinct words, right? And he has to make groups of C words each. So let's say there are a few words. The words are ABC, scalar, right? Interview, bit, right? And edge. So the condition is that the all the words in a group have to start from unique letters, and we have to take C words in one group, right? So we can make a group from these two words, and then we can make a group from these two words. So answer would be 2 for this test case, right? So how can we do this? We can see that the constraints are not very big, so we don't have to worry much about the time complexity, right? So what we can simply do, let's say we have a few words, right? Let's just talk about this example only, right? So what I will do is I will just iterate through the array of words, right? And I will store the count of all the letters from which different words are starting, right? So basically the count of A will be 1, this count of S will be 1, the count of I will be 1, and the count of E will be 1. These are the count of words which are starting from these letters, right? And then what I will do is I will just store these numbers in an array, right? For example, let's assume the example was different and the count for these letters were, this was 3, right? Let's say this was 2, right? And these were 1 and 1. So I will just put all these numbers in the array. So 1, 3, 2, 1, right? Now I will just sort the array so that all the big elements are at the end, right? You will see why I'm sorting this in a minute, okay? So 1, 1, 2, 3. Now I just need two numbers to form a group. So I will just check the rightmost two elements because C is equal to 2. I need two words to form a group, right? So these two numbers, I will take one word from these two letters and I will decrease the count of both of these by 1. Now the array will be 1, 1, 1 and 2, and the answer would be 1 now, right? Again, I will sort this array again. Since this is already sorted, I don't need to do anything, right? Now again, I will take two words and I'm making sure that all the words are starting from different letters. Why? Because all these counts were for different letters, right? Again, I will reduce the count of both these numbers by 1 and increase my answer by 1. The answer would be 2 now, and array would become 1, 1, 0, 1. Now, why am I sorting this? Because all the numbers which are of no use will go to the left side. 0 will be here, and now 1, 1, 1. I'm just making sure that all the numbers on the rightmost side will be the greatest numbers, right? Now I will again form a group from these two numbers. Now answer will become 3, right? And these two numbers will reduce to 0. Now the array will become 0, 1, 0, 0. Again, I will just sort the array 0, 0, 0, 1. Now the rightmost two elements, one of them is 0. Now this will tell me that I cannot make any more groups. That means the answer is 3 for this example, right? So now let's look at how we will implement this method using code. Okay, so this is the code, right? In the beginning, I initialize my array, the count array, by 0, and the size of this array is 26 because there can be at most 26 unique characters, right? And then for all the different strings I have, I just see what is the starting character of that, and I just increment the count of that particular character by 1, right? In the end, I have the count of all the different characters, right? And then I just keep sorting this array and I just keep checking the rightmost C elements until all the last C elements are positive. As soon as the elements become, any of the elements become 0, I will break because I can no longer make groups out of that array, right? And I will just return my answer, right? Now let's move on to the next question. So the second question for the day is unique subarray XORs, right? We have an array A of size n, right? And the question says uniqueness of a set of elements is defined as the number of distinct subset XORs of that set. So for example, if I have this set 1, 2, what are the distinct values, subset XOR values that I can get? So if I choose an empty set, that means if I choose no values, the XOR value would be 0. If I choose just 1, then the value would be 1. If I choose 2, the value would be 2. If I choose both the values 1, 2, the XOR value would be 3. So that means I get 4 unique values. So uniqueness is 4 for this set. right? So we need to find the sum of uniqueness of all the different subarrays of this given array, right? And in the end, I have to take the mod of the answer value with this number, right? So let's take another example. Let's say the array that I have is 1 comma 3 comma 2 comma 5 6 4. Okay, so what would be the brute force approach to do this? I know that there are n square subarrays for an array of size n, right? So what I can do is I can iterate all of those subarrays. For every subarray, try to find the all the different combinations and see how many unique XOR values it can make, and then find the sum, right? But what would be the time complexity of this method? So n square subarrays and another O of n for iterating them, and then how many different combinations it would make? It would be 2 to the power n, right? So this is the time complexity, and then on top of that we also need to figure out what are the unique values. So clearly we can see that this method won't be efficient, right? So what else can we do? How can we improve this complexity? So let's understand a term, basis. Let's see what basis is, right? So let's say I have this set 1 comma 3 comma 2, right? So what would be the basis for this, right? So the basis is 1 comma 2. So basis is basically the least size of a set from which I can make all the elements of this set. So from 1 and 2, I can take both the elements 1 comma 2. I can take XOR of 1 and 2. I can get 3. I can just choose 1, so I'll get 1. I can just choose 2, so I'll get 2, right? So you can see that from 1 comma 2, I can take different combinations, take XOR of those numbers, and get all these different numbers of this set. That makes this set as the basis of the original set, right? So the smallest set which can do this is the basis, and is in this case 1 comma 2 is the smallest set. So that's why it's called the basis of this set, right? So let's say the size of basis is L, right? That will give me 2 to the power L different unique subset XOR values, and that would be the uniqueness of our set. So since for 1 comma 3 comma 2 the size of basis is 2, so uniqueness would be 2 to the power 2, which is 4, right? So for if all the subarrays, I can just find the size of their basis, right? So I can simply find the uniqueness values of all these subarrays, right? So what we'll do is, let me just rewrite this example, right? 1 3 2 5 6 4, right? So what I'll do is, at every point, let's say I am at this point, the 4th position, right? I'll try to find the answer for all the subarrays which are ending at this position, right? So this subarray, this one, and this one. When I'm at the 4th position, I will try to find the answer for all the subarrays which are ending at the 4th position, right? And let's suppose that I would have already calculated the basis of this subarray, and using that, I will now calculate the basis for this full subarray, right? 1 3 2 5, right? So how I will calculate the basis of any set is from right to left. Okay, so let's suppose in the beginning the basis is empty, right? So I'll start iterating from right to left, right? In this case, I'll start from here, right? So the first element I will get is 2. Okay, so I'll see, right now my basis is empty, so should I add 2 to my basis or not? Yes, because 2 is the only element I have in my set right now when I'm iterating from right to left, and this is the first position I get. So obviously 2 needs to be in my set. Okay, so we need to pay attention that we don't need to actually find the actual values which will be in the basis of these elements of this set, because the only thing we need actually is L, which is the size of basis. We only need the size of the basis, not the actual basis, because we are only interested in finding the uniqueness value, which we'll get from 2 to the power L, where L is the set, right? So we only need to see where our basis will be changing, so it will tell me that our size of the basis is changing. So since I know that 2 is going to be added, so I'll just write 2 here, which tells me that the size of basis has changed and it has now increased to 1, right? And I also store the indexes where the size is changing, so that is also 2, right? When I'll reach 3, I'll also check should I add this element to my basis or not. So yes, obviously from the value 2 itself, we cannot make both the numbers 2 and 3. So obviously the size of bases will change. So I'll write 3 here and the position is 1. Okay, again, you need to pay attention here. I am not adding the value 3 to my basis. No, this is just telling me that the value where the size of basis has changed is 3 and the index is 3. Okay, the actual basis would be different. The actual values right now, if you want to look at them, would be 1 comma 2, because when I reached 2, I added 2 to my set because there's only one element. So the element in the original set and the in the basis would be same, right? When I reach 3, I need to add 1 to my set because 1 comma 2, from 1 comma 2 I can make all the elements, 2 as well, 3 as well, and when I'll reach 1 also, I can make 1 also, right? So this is the actual set. These are the actual values which are making the basis, and these are just the positions where the size of basis which is changing. I'm only interested in these because I just need to find in the end what is the value of L. Okay, and finally when I reach the end of this array, I see the value 1 and I see, should I change the value of my basis? No, because the values which are existing in my basis are already enough to make this value as well, right? So my basis just changed at 2 positions. That means the basis size of the basis for this 1 comma 3 comma 2 was 2. Okay, so now let's see how we will use this info to find the basis of the whole array 1 comma 3 comma 2 comma 5. Okay, so I'll start from right to left again. Okay, so let me clear these out. Okay, so now the new set that I have is this one, right? And I start iterating from right to left. Okay, so I get the first element 5. Should I add it to my basis? Yes. So that means the basis changes at this value. The value is 5 and the index is 4. Now we'll see that I have two options. Either I can iterate through this whole array again and for every value check if I need to update my basis or not. And the second option is I have already stored this info right here which represents this whole array because it contains the info where the size of the basis of all these elements were changed. So instead of iterating the whole array, I can just use the elements, the positions where the size of the basis for this array subarray was changed, and I can just simply check for those positions if I should change my subarray or not. Why? Because all these values, let's see, 2, 3, 1, this set, this basis represents those. That's the actual definition of basis. So I don't need to actually iterate the whole array. I can just check at these significant positions which I have stored here. Okay, and how will that benefit us? See, when I was calculating the basis for whole this set, if I had iterated the whole previous set, it would have taken of n time. But now I will only check at those positions where the basis was changed. And how many different spots can be there where basis was changed? The maximum can be of log n, because the size of basis will change at most log n times only. And since I'll do this process at every index of our array, the time complexity would be reduced from of n square to of n log n, right? So now let's look at the code and see how we will implement this. Okay, so this is the code, right? So what I'm doing is in the main function, I'm iterating this for loop from 0 to n, and at each position, I'm using the previous info, the info of the last basis to find the new basis, right? So in the beginning, what I do is, since the last element is not going to be present in the last info, I have to add this in my basis. So I just do use this function add mask to add this variable a of I, this value, in the basis which I'm storing in temp. Okay, and then what I do is I see all the positions, basis dot size, basically all the positions where the basis was changed for the previous array, and I check are those changes needed in this basis as well by using the same function add mask. Okay, so let's take an example. Let's say the array is 2, 1, 3, 5, and let's suppose I'm at the last position right now, right? And I'm using the information from these values to find the new basis for this subarray. And let's suppose the info for the last set was, since I iterated from right to left, it would have been 3, the index would have been 2, and then the basis would have changed at value 1, index 1, right? And when I reach 2, I don't need to update my basis because these two elements are enough to make 2 as well, because I can just take 1s or 3, which is equal to 2. Okay, so this is the info that I have stored, and using this info I'm trying to find the basis of the new array. Okay, so at these positions where the basis was changed, I will just use this function add mask. And after I've calculated the new basis, what I do is I store all these values, the index values, in the new vector v, right? Then I sort it in reverse order. Okay, now how that helps us is, let's suppose the basis was changed at 3 positions, okay, for any set. Let's suppose the size of that subarray was 8, right? And the positions where the basis was changed were 7, 4, and 1, right? These are the positions where the basis was changed. Okay, so I've stored all these indexes in my array v. I've sorted them in decreasing order, and then what I'm doing is I'm calculating the number of subarrays where the size of basis was constant. Now I can see that the size of basis was first changed at this index 7. Before that the basis must have been empty, right? And this must have been the first element, so the size of basis would have become 1 here, and it must have remained 1 till 6th index, 5th index, because it did not change till here. So what I can do is I can just multiply the uniqueness value I get from this into 3. Why? Because the size of basis is the same for all the subarrays containing just the 7th element, the 7th and 6th element, and the 7th and 6th and 5th element, since the size of basis has not changed for all these 3 indexes. That's what I'm doing in this for loop. I just calculate v of j minus 1 minus v of j, that is 7 minus 4. I just check which is the next position where the basis will change. Till then I know that the size is going to be constant, so I'll just take the difference, I find the uniqueness value, and I multiply them. And just like that, I calculate the uniqueness value of all these subarrays, and I just add them, right? And this is the function add mask, using which I see if I have to add any value to my basis or not. So this is a standard way, right? Standard way of doing this. If you want to read more about this, you can read a blog about how we find basis using Gaussian elimination on CodeForces, right? And as we discussed earlier, the time complexity of this method was n log n. Since we are iterating from 0 to n, at each position I'm trying to find the uniqueness values of all these subarrays ending at that position, right? And since I'm using the info of the basis of the last subarray to find the new basis, that takes us a time of log n, right? And the space complexity, since I'm only storing those positions where the basis is changing, and the maximum number of times the basis can change is log n, so space complexity would be log of n, right? So I hope the video was clear. If you liked it, do consider liking the video, sharing the video, and subscribing to the channel for more content like this.